Product of array except self. Want to stand out in any technical interview? Product of array except self is a must-know pattern mastery 100 problem that appears again and again in Phong interviews. Many candidates get tripped up by constraints, like not using division and achieving ON time. If you can solve this one efficiently, you're proving you can handle real-world algorithmic challenges under pressure. Ready to see the trick that interviewers love? Let's go. Let's break down the challenge. You're given an array of numbers. For each position, return the product of all other numbers, except the one at that position. The twist: you can't use division, and you need to do it in ON time. The output is a new array where each index holds this special product. Let's assess our options. A brute force approach would calculate the product for each index separately, ON squared time. Not efficient. Using division would make it ON, but the problem says no division. So how do we do it? The trick is to use prefix products and suffix products. Prefix: product of all numbers to the left of each index. Suffix: product of all numbers to the right of each index. By multiplying the prefix and suffix at each index, we get our answer without ever dividing or missing a value. Here's our structure. Create an output array, initialize to ones. Pass left to right. For each index, multiply the product of all numbers to the left. Prefix: updating the output. Pass right to left. For each index, multiply the product of all numbers to the right. Suffix: updating the output again. The result is the product of everything except self at every index.
Let us try to implement it using solution 1. We begin by defining the solution class. This is the container where our method will live. Then we declare the product except self method. It takes an array of integers and returns another array where each position contains the product of all numbers except the one at that position. Next, we store the length of the array in n. This keeps our code clean and avoids repeatedly calling nums.length. Here we set up 3 arrays. Prefix will hold the product of everything to the left of each index. Suffix will hold the product of everything to the right. Res will store the final result. We initialize the first prefix value to 1 because there is nothing to the left of index 0. Multiplying by 1 keeps the product unchanged, which is perfect for starting off. Next, we fill the prefix array. For each index I, the prefix product is simply the previous prefix value multiplied by the number just before it in the original array. This loop runs in O of n time. After that, we initialize the last suffix value to 1, because nothing exists to the right of the final index. Now we fill the suffix array by moving backward. Each suffix value is formed by multiplying the next suffix value with the number just after it in the original array. This loop also runs in O of n time. From there, we compute the final result. For each index I, the answer is the product of everything to the left, which is prefix at I, multiplied by everything to the right, which is suffix at I. This final pass is another O of n loop. And finally, we return the res array. It is now filled with the correct product except self values for every index. And that is how this algorithm works. It builds prefix and suffix product arrays, then combines them so each position receives the product of all the other elements. Sufficient. Simple. Clear. Check. This test validates the product of array except self logic. Nums equals 1, 2, 3, 4. For each index, we compute the product of all other numbers in the array, excluding the number at that index. We do not use division, so the algorithm relies entirely on prefix and suffix products. Let us verify each position. Index 0. We take the product of 2, 3, and 4. That is 2 times 3 times 4, which equals 24. Index 1. We take the product of 1, 3, and 4. That is 1 times 3 times 4, which equals 12. Index 2. We take the product of 1, 2, and 4. That is 1 times 2 times 4, which equals 8. Index 3. We take the product of 1, 2, and 3. That is 1 times 2 times 3, which equals 6. This gives the final output: 24, 12, 8, 6. The output matches the expected 24, 12, 8, 6. The solution correctly computes the product for each index using prefix and suffix accumulation. Now let us try another implement approach using solution 2. We begin by defining the solution class. This is simply the container for our method. Then we declare the product except self method. It takes an integer array and returns a new array where each position contains the product of all numbers except the one at that position. Next, we grab the length of the input array and store it in n. We also create a variable called suffix, which will hold the running product of everything to the right of each index. We then create our result array, called res. This array will store the final output values. We start by setting the first prefix value in res at index 0 to 1. There is nothing to the left of index 0, so 1 is the neutral starting value. Next, we build all prefix products in a single forward pass. For each index I, from 1 up to n-1, the prefix at I is the previous prefix multiplied by the previous number in nums. This loop runs in O of n time and fills the left product part of our final result. After that, we begin a second loop that moves from right to left, starting at index n-1 and going down to 0. Here we apply suffix products, which represent everything to the right of each index. This also runs in O of n time. At each index I, we multiply res at I by the current suffix value. That combines the prefix product we stored earlier with the suffix product, giving us the full product except self for that index. Then we update suffix by multiplying it with the current number nums at I. That prepares the suffix for the next step to the left. This closes the backward loop. At this point, all prefix and suffix contributions have been folded into the result array. And finally, we return the res array, which now holds the correctly computed product except self values for every index. And that is how this algorithm works. It first builds prefix products in a simple forward pass. Then it folds in the suffix products during a backward sweep, while keeping extra space usage constant. Efficient. Simple. Clear. Check. This test examines how the product of array except self solution behaves when zeros and negative values are involved. Nums equals -1, 1, 0, -3, 3. A 0 in the array significantly affects the result, because any product involving that 0 becomes 0. Let us verify each position. Index 0, value -1. The product of the remaining numbers, which are 1, 0, -3, and 3, includes a 0. So the result at index 0 is 0. Index 1, value 1. The product of the remaining numbers, which are -1, 0, -3, and 3, also includes a 0. So the result at index 1 is 0. Index 2, value 0. Now we take the product of the other numbers, which are -1, 1, -3, and 3. No 0 is involved this time. -1 times 1 times -3 times 3 equals 9. So the result at index 2 is 9. Index 3, value -3. The product of the remaining numbers, which are -1, 1, 0, and 3, includes a 0. So the result at index 3 is 0. Index 4, value 3. The product of the remaining numbers, which are -1, 1, 0, and -3, also includes a 0. So the result at index 4 is 0. So the full output is 0, 0, 9, 0, 0. The actual output matches the expected 0, 0, 9, 0, 0. The algorithm correctly handles the presence of a 0 and the mix of positive and negative values.
Let's have a quick recap. Breakdown recap. So, to wrap this one up, the challenge was to build a new array where each position holds the product of all numbers except itself, without using division. It's a clean, logical problem that tests both array manipulation and optimization skills. Assess recap. We compared approaches and saw that a brute force method would take O(n)² time, far too slow. Division could simplify things, but that's not allowed. The real trick was realizing we could compute everything using prefix and suffix products, one pass from the left, one from the right, all in linear time. Structure recap. The plan was simple but elegant. First, make an array of ones. Then, do two sweeps, one left to right to store the prefix products, and another right to left to multiply in the suffix products. When both passes are done, each position has exactly the product of every number except itself. Implement recap. In code, this came together beautifully. The logic flowed through two clean loops, no division, no nested iterations, and constant extra space. It's efficient, neat, and easy to understand once you see it in action. Check recap. When we ran the example, 1, 2, 3, 4, the result, 24, 12, 8, 6, confirmed everything worked perfectly. All test cases passed. validating both the logic and efficiency. The key takeaway? You don't always need complex data structures, just clever passes and careful thinking. This problem is a reminder that mastering prefix and suffix patterns unlocks a ton of real-world coding efficiency.